abilities of these small humans against our closest primate relatives when solving physical problems corresponding to reasoning about quantities or understanding causality, we perform relatively similarly. It's only in the social domain where we're comparing abilities to do communication and theory of mind that we really beat the competition, that we really distinguish ourselves. And it's this ability to do social learning over multiple generations that allows us to have this unparalleled access to cumulative culture where we can build off of previous innovations, whereas other species seem to have to always begin anew with each generation. And it's this capacity for cumulative culture, not individual intelligence, that is responsible for the success of our species. It's why we can survive anywhere from the Earth's tundra to the Earth's orbit. Yet few of us, despite our big brains, could survive for more than a few days alone in the woods. And one framework in which it's been used quite often to study social learning is a type of collective search problem. So you can imagine a group of agents trying to maximize fitness on some fitness landscape. And this can correspond to a number of real-world domains, such as figuring out technologies, right? So the different dimensions can correspond to different features of some technology that we're trying to develop, figuring out which stock portfolios to buy, or even which type of research to conduct, right? There is some collective search problem with some unknown fitness landscape, and there's often two main pathways of learning. We can do individual innovation, do individual search, individual learning, or we can learn from other people, and the most common method here is social imitation. Right, you can imagine, see in all these cases, we can copy other tools that have been developed, we can copy other people's stock market picks, or we can also be inspired by the research topics. I'm hoping to inspire you today with some of my topics as well. In animal research, a similar type of problem is often studied using a producer-scrounger game, okay? So this is a type of evolutionary game theory dilemma. A producer is someone who's doing individual learning. They're trying to find resources or food or rewards, while scroungers, so this is this unusual English word, but it means to copy from or borrow from others, right? So they're the social learners. They're copying the producers here. So you can, here's an example of what this type of experiment with animals looks like. So here you see that in these little holes, there's different amounts of food pellets. So here, a producer has found a hole that has a food, and these other birds are then scrounging. They're then copying him to then acquire the rewards from the same patch. Now, one of the main dilemmas in both collective search and fitness landscapes and in this producer-scrounger game is figuring out whether to imitate or to innovate, to do social learning or individual learning. And this dilemma is well illustrated by Rogers' paradox. So in the simplest case, let's imagine these individual learners have a fixed fitness, okay? So it doesn't matter what other people are doing, they're always going to have the same kind of rate of reward, same level of fitness. But the social learners in blue here have what's known as frequency-dependent fitness. The fitness of doing social learning depends on what other people in the population are doing. So when I'm the only social learner, right, it's great. There's plenty of people I can copy from, plenty of other producers out there finding new patches that I can imitate. But as the frequency of social learners increases, right, we see there's a sudden collapse in fitness. You're just simply copying other copiers. You're copying noise, right? So there's no real benefit in this situation. And so what Rogers found is that the evolutionarily stable strategy, the ESS, is often some intermediate level, suggesting that successful collectives need to balance the rate or the proportion of individual and social learning. And here we're going to try to see how collectives achieve this balance dynamically and how this adapts to different environments. Now, beyond just the frequency of different strategies, the structure of social learning also shapes the explore-exploit trade-off, which I'm sure many of you are familiar with at the collective level. So in some work back in 2016, me and some colleagues were trying to understand two contradictory results. Some work from Mason and Watts found that fully connected networks of agents perform the best in search on these rugged landscapes, right? So here's the fitness landscape. A bunch of agents have individual social learning strategies, and they're all connected to one another. They can all copy from one another. But also in 2007, Laser and Friedman found actually that these locally connected networks with more restricted flow of information perform best. And here they use these kind of combinatorial NK landscapes. Right. So is it fully connected or is it locally connected networks that perform best? And what we found is that the best network structure depends on the environment, right? So these different classes of environments have different, require different degrees of explore-exploit, right? The best explore-exploit trade-off, it differs between these, and these network structures then determine the amount of explore-exploit at the collective level. And so these fully connected networks lead to faster convergence and faster exploitation, which is beneficial in these rugged landscapes that have these kind of unimodal peaks. But these NK environments, which are very combinatorial and have many more peaks, local optima, require these locally connected networks to maintain greater diversity, right? The restricted flow of information makes sure that different pockets of agents are searching different areas, facilitating more exploration at the group level. And so in this work here, I don't want to use these like predefined and static social network structures, but I want to explore organic social interactions in these dynamic settings. Okay, so this work is also very much inspired by past work that studied collective search in virtual environments in these settings where you can build these organic self-organizing social interactions. But the definition of virtual is somewhat restricted in this past work. So this work by Goldstone and Ashman in 2004, there were these two reward patches. On the very left here, on the very top here, they were equally distributed in 50-50. And then as we move down here, they become more, they have more disparity. So there's one rich patch and one poor patch. In the visible setting, participants could see one another. They're just kind of little dots moving around on the screen. And then in the visible setting, they could not see one another. And then they're trying to see how these collectives search to acquire these rewards, right? So in these patches, rewards were replenished at these different rates, and people had to try to pick them up. And what they found is that in these environments, we see this very systematic cycling behavior where people are using social information and then they're cycling back and forth between the different reward environments. However, so it was definitely one of the first works on search in virtual environments, but it really failed to address some of these kind of more interesting aspects of how people use social information because you have this top-down perspective. Similarly, some work by Peter Kraft and Robert Hawkins studied emergent collective sensing and human participants. So people are these arrows, and they don't see the reward except exactly where they are. And the rewards correspond to these dynamic reward environments where these colors are changing over time. Now, this work is actually inspired by a research studying fish schooling behavior, where schools of fish have been shown to very effectively attract rewards as a collective using very simple rules. Here, participants only see the rewards directly under them, but they can infer whether other people have found higher or lower rewards based on their behavior, right? If other people are spinning in a circle, it probably means that they found a high value reward and they're staying there and you want to copy them. Whereas if someone is moving around quite a lot, you maybe can infer that they haven't found good rewards. This is kind of the state of the art of human, like a search in virtual environments, but it seems to be lacking some really crucial elements, such as kind of more naturalistic incorporation of visual field and spatial trajectories. In contrast, research on animals have had this for much longer, right? So some work by Ariana Strangberg-Peshkin and colleagues were the first to kind of computationally reconstruct the visual field data from these fish, and they show that it provides much better predictions for data. And some theoretical work by Ramani et al. Found that large-scale coordination, also using kind of a fish schooling model, can be improved actually paradoxically by limiting the cognitive capacity of individuals. And in this animal literature, what we see is in a general pattern is that the seemingly maladaptive learning mechanisms, right, that viewed in isolation, very simple learning strategies or limited cognitive capacity can actually give rise to intelligent behavior in these naturalistic and dynamic environments. And here we wanted to set out to find what we could understand about human collective behavior. And to do so, we implemented a collective foraging task using the Minecraft game engine. So in this experiment, people are in a field with these melon blocks, and it's costly to destroy them. And they're trying to acquire these rewards, which are indicated by this blue splash. So there you saw someone just acquire a reward. Rewards are non-replenishing, meaning that you can imitate by moving towards the same area, but not imitate exactly, because that reward is gone. We also manipulate the reward structure. I'll talk a bit more about that later, but here the reward structure is clustered such that when someone finds a reward, there's a high probability of another reward nearby. So the reason that we developed this in this virtual environment is that we have a realistic field of view. This creates an intentional trade-off between focusing on individual search versus looking around at other people to acquire social information. So there's opportunity cost for social information. And we also get these very rich and dynamic social interactions, which we analyze via the spatial position and the trajectories. So we have these really rich spatial trajectories from the task. And we also have access to the gaze data. So we can look at how social information acquired visually informs decisions. And in order to analyze the visual data, what we've done is we've built this automated transcription method. So the way that we program the experiment, it's essentially a mod for the game Minecraft. Children make mods for Minecraft all the time. And we have a data logging module in this mod that kind of keeps track of all the entities, all the player locations, and all the events. This allows us to reconstruct the entire environment using simulations in Unity, where we've mapped each entity, so each block, each player, each reward event to a different RGB value. And then we essentially simulate from each player's perspective using an unlit shader. And then all we have to do is simply read off the pixels on the screen in order to determine whether a specific object or entity or event was visible from a player's perspective at a certain point in time. And then we use this to inform behavioral analyses. We can build things like social networks, directed social networks based on who can see whom. And we can use this to inform our computational model. Any questions at this point? Okay, I'll keep going, but feel free to interrupt. And what we can also do is we can run these analyses on solo rounds as well. So we have a condition where people are performing the task solo, but we can simulate as if they were in the same environment, allowing us to have an asocial baseline for all our analyses. So the main research questions here is that are that we want to understand how do groups collectively negotiate this balance between individual and social learning, right? We showed you via Rogers paradox that often an intermediate mixture is the best, but is it an intermediate mixture based on homogeneous, based on homogeneity where everyone has the same intermediate mixture, or do we acquire this via specialization, where we have people specialized to be individual learners and people specialized to be social learners? We also want to see how people adapt their learning strategies and the social interaction structures to different reward environments, which can alter the balance, the ideal balance between individual and social learning, right? So for instance, inspired by that Ashpole Goldstone study. Okay, so the task begins with interactive tutorial, which I sped up 2 times. People are told how to move around. They can smash blocks by clicking and holding the mouse for 2.25 seconds. They're taught that some blocks contain no rewards and some contain a reward, which is indicated by a blue splash. Participants are essentially incentivized to collect as many rewards as possible. So here people are taught about that here, these green watermelons correspond to cluster reward structures. They were shown this kind of these images showing the overview of the bird's eye perspective of the environment. So the black pixels correspond to rewards, white corresponds to no rewards. So you can see that they're clustered, and they also destroy a small patch to kind of get intuition about what that looks like in practice. And then in random environments, which are here mapped to pumpkins, rewards are completely random. There's no structure. Again, there's shown bird's eye perspectives, and then they destroy a small patch. So crucially, this reward structure manipulation changes the value of social learning. In these smooth environments, when you see someone else acquire a reward, that indicates there's other rewards nearby. So social information is valuable. In this case, you still have to balance it, though, with individual learning. In these random environments, there's absolutely no benefit for social learning. You just want to destroy as many blocks as possible. So after the interactive tutorial, participants have 2 practice rounds. They're solo rounds just to get them familiar with the task. And then we have 16 rounds in a 2x2 design. So we manipulate whether or not they're random or smooth environments. And we manipulate whether or not they perform the task alone or in groups of 4. When they're alone, we essentially make replications of the exact same environment 4 times, and each player is dropped into a different environment. So there's no social interactions there. These are done in blocks of 4 within the same combination of solo or group or random and smooth, just to make sure that there's no learning effects. Some of you might be familiar with an earlier version of this task. I presented this at CarXR 2021. But we only were able to acquire a limited n equals 44 sample due to COVID shutting down in-person testing in Berlin, where this task where we collected data. And since then, we made some minor tweaks and currently have a preprint with a full n equals 128 sample. So some things that we changed in the task. Previously, we had these persistent reward information. So these kind of blue blocks under the reward that were required. We removed this in order to make social information more fleeting. You have to really pay attention to acquire the social information. If you're not paying attention, you don't see someone else acquiring a reward. There's no persistent information about that. We also added these kind of randomized name tags that kind of look like a license plate for people. So this allows for people to be selective of individuals if they chose to, whereas before they were all looked exactly the same, anonymized. And we also simplify the reward animation. So it's just a splash now. Before we had this kind of rocket shoot up to make it more visible, but here we're able to make the splash visible from anywhere on the field. Any questions before I move on to the behavioral results?
Yeah, I might have a question.
Sure.
So for the collective, for the group condition, I wonder, are other people NPC or they are?
They're humans.
Oh, they're humans.
Yeah, so it's 4 people doing the task together in the computer lab.
Okay, so they do this online and they don't know each other.
They're in the lab. This is at the NPI Berlin. They don't know each other beforehand, and they can't see each other's screens. We turn off sound, and so it's only visual information that's possible to find out about the environment.
Okay, yeah, I see. Thank you.
Okay. So I'm going to start with the behavioral results. And one of the first things we wanted to do is try to understand the temporal dynamics of visual spatial interactions. We want to look at how does reward rate, so here's just reward rate overall, the whole population, how does this influence things like spatial distance and social visibility and vice versa, right? So here's average pairwise distance, it changes over time. And here's the average number of visible peers or people who can see you over time. Now, note at the aggregate level, the people you can see, people who can see you, at the group level, it looks exactly the same. But for each individual, they're not symmetric, right? I can look at more people and be seen by less. But at the aggregate, they're the same. Here we want to look at for individuals, how does my performance influence whether or not I change my distance to other people, or whether or not I look more at others, or whether or not I'm observed more by others, and vice versa. So here, these analyses are inspired by methods using EEG and MEG that search for temporally significant clusters in the data. Now, I'll explain what I mean by this. So here's this very kind of cartoon illustration of a reward vector. So this is over 120 seconds. It's the length of a round, and these kind of points where people acquire reward. And here's just some spatial visual vector, right? So either the pairwise distance or the number of people I can see or I'm observed by. Now, what we do is we do different offsets and compute correlations at these different offsets, right? So at negative offsets, I move the spatial visual vector back. We only do correlations for the overlapping regions. And a correlation here would indicate that this vector, the spatial visual vector, predicts future reward. And then in positive offsets, we do the opposite, where reward then predicts these spatial visual features. We then aggregate the data together and identify significant clusters where we do multiple forms of chance correction in order to make sure that these are meaningful patterns. So here I'm going to show you the results, where here relating reward to spatial proximity, so how close you are to other people, reward to visible peers, how many people you can see, so your outbound visibility, and then you reward to observers, so your inbound visibility, how many people can see you. Okay, so just recall that we have these different offsets, and here I'm reporting the temporal correlation z-scored. So any data that's above or below 0 are significant here. Okay, and I've highlighted the significance based on solid lines. So here's the first result. So these solid lines indicate significant clusters in the data. And here what we find is that we see this reward-driven spatial cycling. I'll help you explain, understand how to read this plot. Okay, so in this negative offset regime, where reward predicts future proximity, we see this negative a negative correlation cluster. What this means is that my reward is low. I'm going to move towards other people. My proximity will increase in the future. When reward is high, I'm going to avoid other people. And then as we move to this other side here, what we see is that my reward is low, I move towards other people. And by moving towards other people, we hear about a positive correlation. By moving towards other people, I acquire high reward. But then because I'm acquiring high reward, I'm going to move away from other people. So this is this spatial cycling phenomenon that's only present in these smooth environments where social information is useful and not present in random. And it's also absent in solo condition as well. So we can do the same analysis for the solo condition and we see a very different pattern of behavior. So we see this very adaptive spatial cycling driven by reward. Now here I'm looking at visibility and we see what we call adaptive social attention. So again, here these solid lines are significant clusters. And here what we see is that when people, we have a negative correlation here, meaning that when people have low reward, they're going to look more at other people. When they have high reward, they're going to look less at other people. And this is into the future, right? This is a few seconds into the future, right, that we're predicting here. And so this is suggesting that people are adapting the amount of social attention towards other people based on the reward grades. And again, we have this reversed in solo and it's absent in the random condition. On the right side, we see significant clusters for both environments, suggesting some generic effects of the structure and environment, right? When you're looking at other people, you're acquiring less reward because you're not foraging the blocks. But we also see kind of a more of a pronounced effect in the smooth environment, suggesting that these are opportunity costs, right? When you go to imitate people, you're not destroying any blocks. And lastly, the result here I want to show is that we see significant clusters in the smooth environments, both in negative and positive offset. And what this means is that we see success bias selectivity in social attention. So here, people who have higher rewards are also going to be looked at more by others in the future. But at the same time, people who are observed a lot are also going to acquire rewards at long time scales into the future, suggesting people are very good at identifying people. So they're focusing their attention on people who have been successful in the past, and they're also good at identifying who's going to be successful far into the future. And this is possible based on the structured clusters of rewards. We also have this significant cluster in the random condition, and this is just due to the dynamics of the task, where when you've acquired a reward, the splash temporarily obscures your visibility, right? So that's the only significant cluster here in the random environments. And this is that obscuring also happens in the smooth environments, but it's not a significant cluster for there. Any questions about these analyses? Okay, I'll move on. Yeah.
Yeah, sorry. I might have one question. How did you analyze this distance data? I mean, their trajectories. So did you use
have their spatial location at in 20 hertz resolution. So we every 0.05 seconds, we know their exact position, and we compute the pairwise distance to other players. So proximity is the average distance to other players.
Okay. Yeah, I see.
Yeah. Oh, sorry, inverse distance. Proximity is how close you are. Okay.
Yeah, that's right.
Yeah. Okay. We can also do network analyses where here we've built a proximity network where the edge is equal to the inverse of distance between players. And the visibility network is a directed graph where it's the proportion of time with a single round that another player is visible, right? So we see that we have these asymmetries in this visibility network, whereas this is just an undirected graph in the proximity network. So the first analysis here we found, we looked at the eigenvector centrality. So eigenvector centrality is closely related to things like Google PageRank, where when you're connected to, when you're close to other people who are also well connected, this goes up. And in general, we found the kind of a null or negative trend, right? So just to explain what these mean. So here we do Bayesian mixed effects regressions, controlling for repeat measures of both individuals and groups. So we control for those as random effects. And here important the effect size and then the 95% confidence interval. When this does not overlap with 0, it's significant. Okay, so the top row are the predictors for the solo rounds and the bottom are for the group, right? So in general, we don't see much of an effect, except in the smooth group condition, where we find that centrality predicts higher rewards. And this is perhaps the fact that people are making use of being close to other people in order to then imitate them adaptively when it's beneficial. In these visibility networks, so here on the x-axis, I have in degree, how much I'm seeing. And in the y-axis, I have out degree, which is how much I see others. And here we see that there's some generic asymmetries. So in the random environments, we also see this kind of general asymmetry. But we see that this asymmetry disappears in the solo smooth environments. So this is not significant. And it's amplified in the group solo rounds. And what this suggests is that there's an increased degree of specialization between individuals or people. So when this asymmetry is stronger, people who are being seen the most are not looking at others, and people who are looking the most at others and themselves are not the target of social information. So we get the specialization along this axis. So beyond just only looking at social attention, we also wanted to look at explicit forms of social influence. And in order to do this, we extracted what are called pull events. And this is extracted from movement patterns. And it's inspired by methods used to study wild baboons. And so it's from this methods from the science paper by Ari Stromberg-Persson. So what is a pull event? So first, what we do is we look at different min, max, min sequences and the pairwise distance between participants, right? So here's a minimum, here's a maximum, here's a minimum. So we consider these as candidate pulls. And then we filter by a number of different filters. So first of all, strength, where the change in the distance between these players has to be large relative to the absolute distance. So it's not just a wiggle at a distance, it's a meaningful change in the relative distance to one another. The second filter is disparity. We require that, so that we have two segments from T1 to T2 and from T2 to T3. We require that one player moves more in each segment than the other, right? So that there's that both players are not completely moving together, but that in one segment one player moves more, and in the second another player moves more. So there has to be disparity between the amount of distance that the players move, and then leadership, that one player move more in the first segment and then and move less in the second. So here's an example of one of these pull events where we've categorized these players as being the leader and the follower. So the leader moves more in the first segment, follower moves more in the second. So here's an example at T1. Both of these players are here. At T2, the leader moves all the way over here and has found a new patch. In the same time, this follower has tried to look over here for a reward. Doesn't find anything, turns around, probably observes the leader find a reward. Recall that this only uses spatial movement patterns, not visibility. And then the leader here, the follower here, then moves in to imitate, right? So this is a pull. Okay. We again compute the same analysis using solo rounds as a benchmark. Recall that we can essentially, they're all on replications of the same environment. So we can use this to test the sensitivity of this analysis. And in these solo rounds, essentially have as kind of a benchmark where the structure of the environment leads to some kind of false pulls. But when we compare this to the group rounds, what we see is that we get way more pulls in the smooth environments, and actually less pulls in the random environments. We do Poisson regression, And we see essentially the same result here. And this suggests that social influence adapts to the environment, right? In these smooth environments where it's beneficial to copy others, to use social information, we're seeing larger, many fewer pull events. Even when controlling for kind of these false pulls based on the sensitivity analyses. We can also change the filter thresholds for these different parameters, and we recover the same result as well. Oh yeah, so that's the comparison. Okay. So we also can relate leadership to social attention and spatial proximity. So these pull events are only computed from spatial trajectories, but they relate to visibility as well. So we can compute a leadership score. So essentially, the number of times you've been a leader versus number of times you've been a follower. And this correlates with in degree, right? So leaders are observed more, they observe others less. The difference between in and out degree is larger. And they're also tending to be at the outskirts of the group. So they have lower spatial centrality. But neither leadership nor in or out degree predicts players' overall scores, right? The number of average rewards. Only spatial centrality does. And while leadership doesn't predict overall performance, what we find is that they had higher instantaneous reward rates during pull events, right? So here's the leadership score and your average rewards. There's no real significant effect. But the rewards during a pull event, leaders had much higher rewards. And so it seems to be that social influence is modulated by the success bias at these really fast time scales. So just a quick behavioral summary, we find that social learning is adaptive to the environment and depending on individual performance. We see this reward-driven spatial cycling, and we see adaptive social visibility, where the number of visible peers and observers is predicted by reward rate. And beyond only attention, we also observe more social influence in smooth environments, evidenced by a greater number of pull events. We also see that social learning is specialized. We see greater social attention. We see social attention is directed asymmetrically, but with increased asymmetry in smooth environments. And we also see that social learning is selective. It's directed towards successful individuals and those with low out degree. And while the social learning strategies did not predict overall performance, we find that leaders had higher instantaneous reward rates during pull events, suggesting that there's success bias activity and imitation at these fast timescales. And in order to kind of more directly test for this, here's the part where I introduce our computational models. So here, what we're trying to do with those models is that you've destroyed, right at the point you destroyed your kth block, we're going to predict what your k+1 block you will destroy is going to be. And so we model this as a softmax function over a set of features times weights. So all the remaining blocks will have a set of features, and these features correspond to hypotheses about individual and social learning mechanisms, and I'll talk about that a bit later. And then we have a set of weights that estimate the relative contribution of these different features. And we estimate these weights using hierarchical Bayesian methods to account for individuals and groups as random effects. Right, so we're trying to figure out what features matter for predicting which block is destroyed next, and we figure out which features matter on the basis of weights that are significantly different from zero. So it's a very simple model. We just discretize this into a sequence of block destruction events for each player. So here's an illustration of the model. We're at some midpoint in a round. These are the different players. Their trajectories are these lines following them, and the arrows are their gaze direction. The empty tiles are destroyed blocks that had no reward, and these blue ones are the ones that did have a reward. And we're going to focus on this player here, it's the gray player for the illustration, okay? So here we have a set of features that we use to use our model. We have a set of asocial features that correspond to just the constraints of the task and also individual learning. And then we have social features, which I'll explain shortly. And we then combine them all together into our model predictions based on the inferred weights. And we're trying to predict which choice or which block to destroy next. And here's the actual choice. Okay. So I'm going to start, I'm going to start with the asocial features. So first of all, we have block visibility. We use a very simple visibility calculation, which where yellow corresponds to blocks that are visible from your current position and gaze direction at the time k. Locality is based on inverse distance. You're more likely to destroy blocks near you. So these are just kind of very simple kind of controls for the model. Then we have this individual reward prediction component, and this is based on some of my past work using Gaussian processes to model reward generalization. So many of you maybe know this grid search task in nature of human behavior. It was a bandit task where the rewards are structured, are spatially correlated. So nearby options have similar rewards, and the reward landscape kind of changes smoothly. We've also done this for arbitrary conceptual features like the stripe and tilt frequency of the stripe frequency and tilt of a Gabor patch, which also map onto a 2D reward landscape equivalent to these grids. And we also done this on graph structured environments using a graph kernel as well. But the basic idea is that with a few observations, we can then generalize by interpolating, extrapolating along any arbitrary input space to then try to predict both the expected reward and also our degree of uncertainty, which both kind of contribute to rewards. Here, because we have discrete rewards, you either have a reward or don't, we use the GP, the Gaussian process, to learn some latent variable Z, which is then put through a sigmoid transform, right? So when we have higher Zs, then we have higher probability of reward. And when Z is lower, we have lower probability of reward. So we essentially applied this to the same task, and it's a rational individual learning model that's also been confirmed in a number of my past studies. So here for this player, the blue is the blocks that they destroyed that had a reward, and these kind of outlined blocks are the ones that they destroyed that did not have a reward, and this forms the basis for this GP prediction, right? So here, essentially, it accounts for the correlation structure in the environment as an individual learning mechanism. For the social features here, we use our annotation in the visual field. So between k minus 1 to time k, we go through the visual fields and we essentially determine which players are visible. Okay, so given that players are visible in this time frame, which players observed being successful and which players are observed being unsuccessful. So then we categorize them into two separate categories of features based on proximity. And proximity is based on the centroid of their last observed location, based on this visibility data. And so here we have this player was observed being successful, and we have success proximity. And here this player was not observed being successful. This is unsuccessful proximity. And we essentially are able to compute different weights for this model. So I'll just give it away, or maybe I'll skip ahead just a little bit. So here's a model comparison. I should have started with this first. So the success bias model is the winning one, which I just described. We also included a couple alternatives, such as an asocial model that had no social information, an unbiased model that made no distinction between successful and unsuccessful players. And then we also fit a player-specific model where people could have unique player-specific proximity weights for each of the other players, which is fit hierarchically and can get groups for each player estimated from the other three players. And so the success bias model, which I described to you, is the winning model, although we have some kind of non-trivial variants also by the player-specific one as well. I don't think I have time for it, but we can also relate that to a whole wide range of interesting variables. So just to explain the model results. So here are the weights that we estimated hierarchically using Stan, and I'll explain a little bit what they mean. So first of all, the block visibility and locality, they matter in all conditions, right? Just purely constraints of the task, but they're typically stronger in random than in smooth environments, because in the random environments, there's an absence of reward predictive cues. The GP predictions are strongest in the smooth environments, of course, and then null or negligible in random, right? So the GP is essentially assuming the true structure in the smooth environment, and so of course it doesn't really capture the random environments very well. In the social features, we see that social successful players attract much more in the smooth condition, and unsuccessful players exert no influence. I should also mention that even though this is much less than the smooth environments, successful players still attract to some degree, and to a significant degree in the random environments as well. Sorry. We also observed from the model weights increased specialization and group diversity in the smooth environments. So here, what I'm showing is the distribution of the absolute difference between the social and individual learning weights. So we look at the difference between these weights, and then this density plot here shows you the difference between smooth and random, where we see an increase in the difference between social and individual learning weights. So we see that greater specialization of players. And we also see greater group diversity as well in smooth environments. We see greater variability in the difference between social and individual learning weights. I'm running a bit short on time, so I'm going to kind of quickly rush to the end. We also do a bunch of agent-based simulations. So these are kind of a simplification of the task where we can program these agents based on the different models. They're selecting a destination based on the softmax, navigating there, and these lines correspond to visibility when players can see one another. And we can recover that there's the same benefit for the success bias model in the, I'm missing a title here, in the smooth environments, but not the random environments. And just to get to the end, I want to mention a couple limitations and future directions before my summary. This experiment was actually originally designed for VR. We actually had some tests of this already. This is in German, but the issue is that locomotion in VR relies on short-range teleportation to minimize motion sickness. And this produced unrealistic spatial trajectories in testing, and also temporarily obscures visibility, which is a key part of the analyses. So this is my current VR lab here in Tübingen. I'm currently working on some follow-up experiments using a swimming as a locomotion. You can be seated and move your controllers like this, and that minimizes VR sickness to a great degree. Here, I focus only on the simplest form of social learning, which is imitation. Some theoretical work I've published last year also creates this kind of hierarchy of different forms of social learning. We can directly imitate people's actions, but we can also use those actions to infer things like their value representations or their model-based beliefs about the world. So some work in my lab is currently looking at how we arbitrate between these different social learning strategies. So we have this social transit inference task. There's a bunch of cards with a hidden value ordering. And the demonstrator is going to pick a card that they, based on the true knowledge of the value structure, and the participant will be dealt a different set of cards. They can always imitate. They can essentially use value inference to infer, hang on, based on my previous knowledge, this hat is better than car, so I'm going to choose hat. But as well, at some point in the task, the value ordering flips. And so having seen the demonstrator regularly prefer this side of the hierarchy at first, but then all of a sudden switch to this, you might then infer that a switch has occurred. And I'm going to then take what I previously learned to be the lowest valued option and then select it because it's now the highest. So this is a form of model-based inference. So this is getting at kind of much more complex theory of mind-based representations. I think I'm out of time to talk about this project, but I will then just go to the summary. So here I've shown you the really rich behavioral tasks that social learning is highly adaptive, specialized, and selective. People adapt to the environment and their individual performance. They specialize within groups through asymmetric social learning, and they have success by selectivity and social imitation. Behavioral analyses capture the temporal dynamics and the structure of these social interactions, and computational models directly test different mechanisms within a unified framework for sequentially predicting foraging decisions. You have a couple open questions you wanted to ask about. This asymmetry of social learning, we speculate, could potentially be a safeguard against maladaptive herding, right? So instead of copiers copying other copiers, what we see is that social learning is selectively directed towards individual learners with low out degree. And this asymmetry then protects against this kind of information cascade that leads to maladaptive herding. We also see that success bias is still present in the random environments, even though it's substantially reduced. And perhaps this could be a limitation of human adaptability. But also, social imitation could be a computationally cheap tool for engaging in exploration, such as like in an exploration device. Exploration is costly, right? So my work, among others, have shown that putting people under working memory load or time pressure reduces their ability to do directed exploration. And so here, what you can do by imitating people, you're just using them as a way to kind of get another, do better exploration. And it seems kind of maladaptive, but it's potentially a boundedly rational solution. So thanks to my collaborators on this project, and I can open the floor for questions.
Okay, thank you, Charlie. Very substantial work. I'm very deeply impressed by your work, and I think I cannot imagine this is from one paper. So very fantastic. And I suggest we unmute ourselves and give Charlie a round of applause. Thank you very much. Well, it's time for questions and discussions. So okay, yeah, we have one question from Hanbo.
That could also be a clap, but
yeah, just go ahead, unmute yourself and ask your questions.
Yeah, I just hi Charlie. So thank you for your great talk, and I feel very impressed. It's even within the same paper. So just starting from the conclusion, so you mean the success bias, is kind of like a wide range of how people actually adopt such a strategy in the social learning dilemma. That actually reminds me of that another paper of Thomas Gray's paper in Science. So you probably heard of that. It's about generation by generation social learning. So just like people always like to choose those with higher performance in the last generation, but that does not necessarily mean they can actually learn very useful information and yield a higher performance than the last generation. So I totally agree with you, the conclusion that sometimes learning from better ones or more successful ones is not always, or it's not just useful for learning, and probably we just need to think about some strategies, just like a balance before that.
Yeah. So I guess here, like, imitation is not trivial, right? Because you can't imitate their exact solution. Once they've destroyed a block, it's gone, right? So here you can only do imitation with innovation on top of it as well, right?
Yeah.
And also, when you're going to imitate, we weren't necessarily expecting that we would have this type of bias imitation, because then you also have to then compete with them for the same limited resources, right? But nevertheless, we still see it here. So I think in Tom's transition chain experiment, imitation is a very safe strategy, but here it's actually more of a risky one, because then you actually have to then compete with those other people in the same area.
Yeah.
Right. But nevertheless, it's still an effective strategy. We can demonstrate this through age-based simulations, that it's a better strategy. And we also see that it contributes to people's, it's a big driver of performance here.
Yeah. Thank you, Charlie.
You're welcome.
Anyone else? Or just type your questions in the chat box if you don't want to unmute yourself. Yeah, Charlie. Charlie, I might have one question about STEM. So I wonder, how long does it take to fit your model in STEM? I think I can.
It's like 2-3 days. Oh, actually, it's a bit faster now, because they at one point they introduced the ability to parallelize across chains, right? So we can do distributed computations
yeah,
for a single model. So that actually sped it up to about a day. Yeah.
Okay. That's a lot of time. Yeah. And so I might have another question. So I'm also running the virtual reality experiments myself currently, and I might miss you. So why don't you ask people to move in your virtual reality? So
we have a limited space, right? So like, for instance, here we have like a 4x3 meter tracking area. And then you have a very limited space. Like, our field is massive, right? I forget the exact size, but I think it's like 20. It's like, no, so there's a space between each block, right? So each block essentially occupies about like a 3x3 space. So it's like it's like 60 by 60 meters, right? A block is about a meter in Minecraft, right? So 60 meters by 60 meters is the full space. In the actual like scanning area we have, you only have a small fraction of the space. Right, so we don't get these kind of really rich spatial trajectories. You can have people stand, but then use the motion control, use the joystick to move, but then we have motion sickness issues. Right?
Okay.
A lot of people have motion sickness. So this is why the swimming thing seems quite promising, because I can get people to sit and they can move their arms like this as if they're swimming. And that movement helps mitigate motion sickness.
Yeah. So it's actually a practicality issue.
Yeah. Yes,
Okay.
exactly.
Okay, I see. Yeah, it's very charming. And have you, how to say, put your task open source?
Yeah, we're planning on doing this like once the paper gets further through the review process. There's just a bit of work cleaning up. It's actually quite straightforward. It's just a JavaScript module.
Yeah, because I'm very excited to try your VR game myself.
Yeah, okay. Yeah, like, and also we designed this to be completely for VR, right? So essentially with Vive Graph, you just plug in with VR. We even collected some data during testing, but just like with the teleportation, we just don't get realistic trajectories. And we also lose visibility during the movement event, right? Which interferes with the analysis that we wanted to do here.
Okay, I see. Yeah. Anyone else? Any questions, or you would like to ask Charlie for clarifications?
Yeah, I'm sure there's something that people didn't understand, so don't be afraid.
Yeah, I'm also sure. So yeah, just unmute yourself or okay, so I maybe have another question. So regarding your models, I'm curious, you mentioned about the weight, and could you clarify how did you compute the weight in your model?
Right, so the weights are computed hierarchically, right? So we account for that individual, so we get repeat measures, right? So there's random and solo, random smooth and solo and group. So we get repeat measures from individuals. So individuals are hierarchically grouped, right? So within different conditions, we expect the individual to be consistent. And then we also have hierarchical random effects for groups. So we expect groups to be more similar to one another than different groups. And so then these here are the population level posteriors, right? So when they're different from zero, they're meaningful.
Yeah. Okay, I got you.
Yeah. And then all the weights then contribute to the softmax, right? So the higher the weight, the more influence that feature has on prediction choices.
So which means, in other words, these weights are actually the varying or the random effects from the individuals, from the group conditions.
No, these are not the random effects. So these are after accounting for random effects, these are the population level posteriors.
Okay.
We account for the fact that there are random effects as well. Yeah, and this is what remains in the aggregate.
Okay, I see. Yeah. Yeah, so I guess there's no more questions. Would you mind people to mail you for further questions or discussions?
That sounds good. I think my email's on the first slide. Oh, no, it's not, but you can find it from my lab website, hmclab.com.
Yeah, of course. Okay, then Charlie, thank you for joining us today. Yeah, and also everyone, thank you for your joining, and have a nice day.
Okay, take care. Bye.
Yeah.
Thank you, Charlie. Bye.